Okay, this is Solutions Lesson 2. The objectives of today's lesson are to define solubility and understand the factors that contribute to solubility, such as the nature of the solute and solvent. We'll review like dissolves like, temperature, and possibly using Table F to determine if a precipitate is formed in a chemical reaction. We're going to distinguish between a saturated, unsaturated, and supersaturated solution, and we're going to learn how to read solubility curves to determine if said solution is saturated, unsaturated, or supersaturated, and then differentiate between dilute and concentrated. So last night's video left off with characteristics of solutions. So let's review. First, we know that all solutions are homogeneous mixtures, which means that they are consistent throughout, and remember that they can be separated by physical means. They are clear or colored as opposed to cloudy. They can be colored though, and they do not disperse light, meaning no Tyndall effect is observed. And I'm going to review what that is in just a moment. They can have color, as I just said, or be colorless. And very importantly, they do not settle if left to stand, no matter how long the time is. Unlike a heterogeneous mixture, specifically a suspension, if I have a jar of muddy water and I let it sit, after time you'll see the sediment will separate and go to the bottom. And homogeneous mixtures cannot be separated by filtration. And a good example here is salt water. I can't get the salt out of the water by filtration. I have to use other physical means. So what is Tyndall effect? Tyndall effect, first of all, is not seen in solutions. It is seen only when a mixture makes a beam of light visible. So in this example right here, when the laser light is projected through a mixture, if you can see the light, you know it is not a solution. Okay, in figure 1 here, this shows the example of a Tyndall effect, with the top being of a humidifier and steam coming out, and you can see the laser light beam that's produced when projected at the steam. Tyndall effect is not seen in a pure solution. It has to be something other. It has to be either a suspension of some type. Okay, phase of solute, phase of solvent, and let's try to give an example. So remember, your solute is what's being dissolved, your solvent is what's doing the dissolving. So if my solute is in the solid phase and my solvent is all in the solid phase, I'm talking about two solids. And the example that we used in our notes was an alloy. So bronze, steel, any of those. In the next one, my phase of solute is solid. My phase of solvent is liquid. So if I have a solid in a liquid, this would be an example of salt water. If I have a liquid in a liquid, so let's just say that I'm making an acid solution and I'm starting with 12 molar hydrochloric acid and I'm adding it to water to dilute it maybe down to 6 molar. So we could have hydrochloric acid in water. So I'm just going to put hydrochloric acid aqueous because that means mixed with water. Or I might have ethanol, which is alcohol, aqueous, also mixed with water. If I have a gas and a liquid, a good one for an example would be just soda, either club soda or Coca-Cola. You've got compressed CO2 in the liquid, and a gas in a gas. A good example might be air. As I just mentioned, the solute is the substances or substance that are dissolved in a solution. For example, the salt in the water. So the salt would be the solute. The solute is usually, in most cases, a solid and is the lesser quantity of the two items being mixed. The solvent is the substance that is dissolving the solute. So again, using the same example of salt water, it's the water in the salt water. The solvent is usually a liquid and is usually the greater quantity of the two items being mixed. So in the example below here, my solute, although it is a liquid, okay, in this case, is in an eyedropper, and I'm adding that to the solvent, which is the larger quantity in the bottle, and that equals a solution. This whole process is called solvation. Not salvation, but solvation. So, aqueous, a solution in which water is the solvent. So, for example, NaCl is otherwise known as salt water. But when we really look at it under a microscope, okay, I have Na plus ions that are aqueous, and I have Cl minus ions that are aqueous. And let's review what happens when I put salt in a beaker of water. So if this is my beaker of water down here, okay, and remember I have water molecules in here. I'm going to draw a couple of them just so you can see this. And what happens when I put solid sodium chloride in here, the NaCl separates into ions. Remember that the oxygen side of the water molecule has got a partial negative charge, while the hydrogen has a partial positive charge. And remember that opposite charges attract. So when I drop that NaCl in here, we know that the chlorine, being the negative ion, is going to be attracted to the positive hydrogen side, and the Na, which is positive, is going to be attracted to the oxygen, the negative side. And that's what happens when we put salt in water. And so you have these free-floating ions in solution attracted to either side of the water molecule. Okay, we're getting ready to talk about table G, which is our solubility table, but we have to understand three pretty important words: unsaturated, saturated, and supersaturated. An unsaturated solution is one in which more solute could be dissolved in the given amount of volume that you have, where saturated is a solution containing the maximum amount of solute, abbreviate amount, that will dissolve in a given volume of solvent. So if a saturated solution contains the maximum amount, this is also known as solution equilibrium. So here's an example of the two solutions that we just talked about. The top solution is an unsaturated solution. I have 100 mils of water in the beaker on the right, and I'm going to add 30 grams of NaCl. So this gets dumped in here, and plus I have the 30 grams of NaCl in here. That's my solution. All of that dissolves. Notice that there's nothing left on the bottom. That's an unsaturated solution. What that really means is that I could still add a little bit more than the 30 grams of NaCl. In this bottom, I have a saturated solution. I'm going to add 40 grams to this 100 mils of water. And notice over here on the right, a little bit didn't dissolve. Stirred and stirred and stirred, and what happened was this wound up being 100 mils of water and 36 grams of NaCl. This is saturated. It holds the max amount of grams of NaCl for the given volume of water. The 4 grams would not dissolve. A supersaturated solution is a solution that contains more solute than could possibly ever dissolve in that particular amount of volume. And it usually requires an increase in temperature or pressure initially to even get the solute to dissolve. These types of solutions are very unstable, and I'm going to demonstrate this in class. Very unstable. One slight change and it could be catastrophic, and all of the solute could come out of solution. Okay, so let's review some situations. If you have an unsaturated solution and you add crystals, what do you think will happen? Well, remember, unsaturated means that it can hold more. So crystals will dissolve. Or disappear. Because if they dissolve, they disappear. The rate of dissolving is greater than the rate of precipitation. If you have a supersaturated solution and you add crystals, what's going to happen? Well, as I told you, supersaturated can't hold anymore. It's beyond the limit. So all crystals will precipitate out. And whenever you see me use PPT, please know that that means precipitate. I will use it a lot in this unit, and I don't write out the whole word. If you have a saturated solution and you add crystals, what will you observe? Well, if it's saturated, most of the crystals will dissolve, and then few crystals will sink to the bottom. The rate of dissolving is equal to the rate of precipitation. Remember, we said that a saturated solution is solution equilibrium. I see I left one blank. In a supersaturated solution, the rate of dissolving is less than the rate of precipitation because everything precipitates out. Okay, let's talk about Table G. A couple of things you need to know about Table G before we get started. It's easy to use if you understand it, but you have to be exact as possible. The Regents scorers only usually allow plus or minus 1 gram. So if the answer is 35, they'll take 34, 35, or 36. So if you need to draw a line so that you can be as accurate as possible. The other common mistake that often happens in this section is that students that think that they're looking at one substance when they're really looking at another. It's very easy when you're reading the question for your eyes to deter from the line that you're actually looking at, and the next thing you know you're looking at another line, which causes you to get the wrong answer. So just a few of those pieces of information before we get started to help you be more successful in this section. So how do we use Table G? Well, first of all, I need to show you that this is going to tell you the number of grams for each substance that will dissolve in 100 grams of water at a given temperature. Now, why am I circling 100 grams? Because the reagents will change the grams of the water, which means that you have to make that adjustment in your final answer. So as I said, this was 100 grams of water at temperatures between 1 degree and 100 degrees Celsius. Each curve represents the maximum amount of a substance that can be dissolved at a given temperature. All lines that show an increase in solubility as temperature increases represents what? So as you can see, all of these positive slopes, NaNO3, Ki, KNO3, NH4Cl, they're all a positive slope. They represent solids. Okay? Think about it. If you had cold iced tea and a cup of hot tea, which one could you dissolve more sugar in? Well, absolutely the hot tea. Because with a solid, as temperature increases, solubility increases. So I'm just going to rewrite that down here. Solids, as T increases, solubility increases. Now, we have a few on here that have a negative slope. HCl is one, NH3 is another, and SO2 is the third. So the lines for those slope downward. So the lines for gases. So for a gas, okay, I'm going to write this down here, gases, as temperature increases, solubility decreases. And you know this for sure because we've talked about whether you have a glass of cold soda versus a glass of warm soda. Which one's going to have more carbonation? Well, the glass of cold soda, because if you leave a glass of soda in the hot sun causes the molecules to move faster, they collide more, and they come out of solution. All right, so how do I tell if something is saturated, unsaturated, or supersaturated using Table G? Okay, so if the intersection of grams versus solute, so what they're talking about here is the data point. Okay, so if the data point is on the line, then it is saturated. So I'm going to give you an example of this. We're going to label this number 1. So right here, let's pick this one right here. 10 degrees Celsius, 70 grams, and this is NH3. So this is NH3, 70 degrees Celsius, 10 grams. The data point is on the line, therefore it is a saturated solution. If it is under the line, then the solution is unsaturated. I'm going to give you an example of this using a different color. So number 2, I'm going to pick this point right here, and I'm going to reference this to NaNO3. So we have NaNO3, 30 degrees, 80 grams. 30 degrees Celsius, 80 grams. Notice how the data point is under the line, therefore this would be considered an unsaturated solution. And if it is above the line, the solution is supersaturated. And we'll call this number 3. put this one right here in reference to NH4Cl. So this is NH4Cl at 60 degrees and 80 grams. So notice how this data point is above the NH4Cl line. It would be considered a supersaturated solution. Okay, we're almost done. The last thing we're going to do is run through a couple of these practice problems, and then that's it. Okay. So let's look at the first question. How many grams of NaCl will dissolve in 100 grams of water? So my grams of water are the same. I don't have to make any adjustments at 90 degrees. So I'm going to go to 90 degrees, and I'm going to see where it intersects NaCl, and I'm going to put a dot. So that's 90 degrees NaCl, and when I read across, that is 40 grams. Okay? I go up from 90 degrees, see where it intersects NaCl, put my dot, and follow that all the way across, and it's on the 40 gram mark. Number 2, how many grams of KCl will dissolve in 50 grams of water? Anytime you get a question that changes the volume of water from 100, it could make it less than 100 or it could make it more than 100. The first thing you're going to do is solve for it as if it were 100. So, how many grams of KCl will dissolve in, let's say, 100 grams of water at 30 degrees? So I'm going to go to 30 degrees. I'm going to see where it intersects KCl, which is right there. And I'm going to go over and I'm going to read those grams. So it's probably about 36, so it's a little bit more than half. So the first thing I'm going to write down is 36 grams in 100 grams of H2O. The question is asking about 50 grams of water. There's two ways I can solve this. First way is intuitively. Half of 36. Did I read that right? Okay. Half of 36 is 18. So 18 grams of KCl in 50 grams of water. Or I can set up a proportion. So I know that I have 36 grams in 100 grams of H2O. Therefore, how many grams will I have in 50 grams of water? And I can cross multiply and divide, and I'm going to get the same answer. And the last question, how many grams of KCl will dissolve in 200 grams of water at 30 degrees? So I'm going to go to 30 degrees, and I'm going to solve it for 100, which we just did. We said it was 36. I'm going to solve this one up here. So it's 36 grams in 100 grams of water. Intuitively, if it's asking about 200 grams of water, I know I have to double it, which would make this 72 grams in 200 grams of water. And that would be my answer. Or I can set up my proportion, 36 grams in 100 grams of water equals X grams in 200 grams of water. And I'd still get the same answer. It's just whatever you prefer, your method of solving. Okay, let's go to some more questions. These are the last 5 questions of the lesson. Name 2 substances on table G that are solids. Remember we said that as we increase temperature, we increase solubility for a solid. So I could list anything here that has a positive slope. I can list Ki, I can list KNO3. Let's list all of them. NaNO3, NH4Cl, KCl, NaCl, even though that it's only a very slight positive curve, it still counts, and KClO3. So 7 of them. Name 2 substances on the table that are gases. So these had a positive slope. These are going to have a negative slope. So there's only 3, SO2, NH3, and HCl. Is a solution that is made up of 100 grams of water and 70 grams of KNO3 at 50 degrees saturated, unsaturated, or supersaturated. So we're dealing with the normal amount of water, which is always good, and we're going to go to 50 degrees and we're going to put a mark at 70 grams. So there's our 50 degrees, 70 grams. And now we're going to find our KNO3 line, which is right here. And we can see that this data point is below the line, which means that this is an unsaturated solution. And how do we know? Well, because if we were to continue up at 50 degrees to see where it does intersect KNO3, it intersects KNO3 right about there, which is probably about 84 grams. So you could say it's unsaturated because at 50 degrees Celsius, KNO3 can hold 83 grams, or maximum solute, in 100 grams of water. Okay, next question. At 40 degrees Celsius, if 100 grams of KNO3 are added to 100 grams of water, so we're dealing with normal water again, how many grams of solute will fall to the bottom of the solution? When you see the words fall to the bottom of the solution, that's the same thing as saying precipitate. How many grams will precipitate? So 40 degrees, and we have 100 grams. So I'm going to go to 40 degrees and I'm going to put a mark at 100 grams, which is right here. I'm going to look at that in relation to KNO3. KNO3, this is above the KNO3 line, so we know it's supersaturated. It can't simply hold that much. And at 40 degrees, KNO3 can hold approximately 65 grams. So it has 100 grams in it. It can really only hold 65. So the difference is the amount that will precipitate out, which is approximately 35 grams will precipitate. And the last question, which is more concentrated on table G, point A or point B? When we talk about concentration in terms of solutions, it's basically the amount of solute so it's the amount of solute over the amount of solvent. So when we look at point A, which is right here, and we compare it to point B, the one thing that we notice is that they're both at the same temperature. So they're both at about 45 degrees Celsius. However, A has 130 grams per 100 grams of water, and B has approximately 100 grams per 100 grams of water. So we can definitely say that A is more concentrated. So this one is more concentrated. One last point of interest. Usually we say that unsaturated solutions are dilute because they could hold more solute, and supersaturated solutions are usually referenced with the word concentrated. And saturated solutions are just right, as Goldilocks says. And that's when we have solution equilibrium. All right, see you tomorrow for lesson 3.